And before we lose everyone, let's go to the last presentation of this session and of the morning, and it's by Merlijn Blaauw. Merlijn is a researcher working here at the UPF, at the MTG, working in singing voice. We have been working on singing voice in collaboration with Yamaha for a long time. And recently, of course, we had to work on deep learning for that, and they got some very, very good results that I don't think in the singing voice they were not possible until now. So let's hear Merlijn. All yours.
Okay, thank you very much. So I'm presenting some work on neural singing synthesis that we've been doing lately, and it's a work together with Jordi Bonada. And so to give a little bit of background, Xavier already told you, but it's singing synthesis is a very long-running research topic here at the Music Technology Group, thanks to a collaboration with Yamaha in Japan. And the main outcome of this research is a product called Vocaloid. And this has been quite successful, especially since one of the virtual pop idols called Hatsune Miku, it's actually misspelled here, went viral in Japan around 2008 to 2010. And it really generated a lot of interest and activity. So there are many, many compositions, including top 10 albums, videos with millions of views, concerts, merchandising, video games. So it's quite amazing what happened with this technology. So this Vocaloid technology is based on quite old technique that we already saw in the keynote. So it's diphone concatenative synthesis, and the pros here that sound quality can be quite good with a lot of work, and it has been state of the art for a long time. But the drawbacks are that we cannot use very expressive singing to build these kind of synthesizers. So what we do instead is use something called pseudo singing, which is kind of in between speech and singing. I can play a small example.
Exnupcial, mejor dicho.
So because we use this kind of data, these systems are not very good at modeling expression. And also creating the voices tends to be a lot of work, and they tend to work better for languages like Japanese or Spanish compared to English, which is a bit more complicated in terms of phonetics. So to hopefully solve most of these problems, we started working on deep learning. So we have a system which we call the Neural Parametric Singing Synthesizer, or MPSS, which we presented at Interspeech in 2017. And it's based on WaveNet, which we already saw. And just to sum up a little bit, it's a revolutionary improvement in the text-to-speech field. And it's an autoregressive model of the speech waveform conditioned on linguistic features based on a smart convolutional architecture. And at the time, the main drawbacks were slow inference, and it was kind of low-fi, so only 8-bit and 16 kilohertz. However, unlike WaveNet, MPSS uses vocoder features. And in this case, the vocoder is a DSP algorithm that separates the signal into pitch, timbre, and aperiodicity. So why use vocoder features, which might seem like going a bit back? So the main reason is improved data efficiency. So in this case, we can model pitch and timbre separately. And also, while this is a more traditional approach that in the past had kind of subpar results, we argue that this was mainly because of the model used, so for instance HMM, rather than the vocoder itself. So if you just take a sample and you analyze it and resynthesize it, the quality is quite good. And if we want to, we could combine this MPSS system with a neural vocoder or WaveNet vocoder and generate the waveform from vocoder features with higher quality. And while it wasn't really the main goal, it has some additional benefits. So the inference is much faster, so maybe 10 to 20 times real time on a single core CPU. And there are no issues with sample rate or bit depth. So this allows, for instance, to implement it in a web servers or on a mobile or something like that. So the main change we made to WaveNet is that the data we have to process is 2D instead of 1D waveform. So how we do this is in the CNN framework, we process the 2D data as 1D data with multiple channels, and then use an independent output distribution for each of the channels. And here we should note that while the output channels are independent, each prediction is conditioned on all channels of the previous time steps. So there is quite a lot of interaction between the different channels. And also a difference is that WaveNet uses categorical or softmax output over discretized data, but this approach becomes quite impractical once we have a lot of dimensions. So instead what we do is simply use a continuous distribution, and generally a unimodel one, so just a Gaussian or Laplace, or we have something called a constrained Gaussian mixture, which you can see there in the plots, allows some different shapes, but is still a single mode. And another kind of important detail, kind of implementation detail that was needed to just get it to work, is that because the vocoder features are a lot less structured compared to a waveform, for instance, you can see there in the plot the difference. What would happen during training is that the model becomes overly reliant on past time steps to make the predictions. And in this case, it can kind of ignore the control inputs, so change the lyrics, and also poorly handle accumulated prediction errors during synthesis. And the solution we use is, instead of conditioning the model on past time steps, we condition the model on corrupted past time steps by simply adding Gaussian noise. So just to illustrate this, if we do not add this noise, we get something like this. So quite horrible. And then if we add this noise, we get something like this.
Buscando un corazón.
So already a little bit better. So in this first publication in Interspeech, the model we had only models timbre, so not page or phonetic timings, and those have to be given as control inputs. And so I will play some demos, and in this case, these kind of control inputs were extracted from a reference recording. So first a Spanish demo.
Siempre serás bienvenido a este lugar, a mi lista de obsesiones.
And also an English demo, and in this case we do apply this technique of adding a WaveNet vocoder to the end of to the output of the MPSS synthesizer.
I sit and talk to God, and he just laughs at my plans. But he speaks a language I don't understand. I just wanna feel.
Okay, so of course having to use a reference recording for page and timing is quite a big limitation. So in the same year we extended this publication for a journal, where we made a complete synthesizer. So we include some modules for page and for phonetic timing prediction. And in this case, the input is kind of like a MIDI-like musical score, and lyrics with, in this case, phonetic lyrics. So we'll play a demo in Japanese. So in this case, the model, for instance, decides where to put vibrato, how to do the transitions between the notes and things like that. So in the results of this work in listening tests are basically that it outperforms previous systems based on unit selection or HMM synthesis. However, there's still quite a big gap between actual real singing and our system. So we're not quite there yet, but getting closer. And the final topic I wanted to talk about a little is singing voice cloning, which we submitted to ICASP. So this MPSS system, to create a voice, we need at least like 30 minutes of recordings. But there are many applications, especially in singing voice, where we want to do this with less data. So maybe we just have 1 or 2 songs of the voice we want to create. And in this case, we can use these voice cloning techniques, which allow to do this, but by leveraging data from additional speakers. And these techniques have already been quite successful in text-to-speech, especially in the last year. There have been a lot of different publications that do this. So the technique we use is first create a base model trained on many different speakers together, and then each of the different speakers has its own embedding vector, a speaker embedding vector, on which we condition the model. And this speaker embedding is jointly learned when optimizing the model. So once we have this base model, we adapt it to a target speaker by first finding the speaker embedding corresponding to this new speaker. Also just by optimization, and then after that we we apply some fine-tuning of all the model parameters to better match the target, and in this case we apply some early stopping to avoid overfitting to the small amount of target data. And one potential issue specific to singing is that there can be quite a lot of change in the voice of a singer within one song or between different songs. So in this case, having a single speaker embedding is not really appropriate. So a kind of practical approach we used here is to create the base voice, so the multi-speaker model, using this pseudo singing, and then adapt to natural singing. So just to give an example, so the multi-speaker model might be trained on data like this. Oops.
Rapid brown, avoid clear blue.
So very consistent Korean data. And then the adaptation data might be something like this.
All the scars that won't heal, your eyes have died.
So these techniques in the listening test, they're rated, the voices created by cloning are rated on par with voices created from full data sets, and much better than the voices created just from the very small amount of data. So just to play a couple of examples. So first is a Japanese demo where we have 35 speakers for the multi-speaker model, and then 2 minutes of the target voice.
改札の前つなぐ手と手いつものざわめき
And kind of the same thing for English, but using only 13 speakers for the multi-speaker model and 2 complete songs for the target data.
There must be some kind of way out of here. Say the joker to the thief. There's too much confusion. I can't get no relief.
Okay, and finally, another kind of use case of this cloning technique is the idea to do choir synthesis, and maybe you want to create a very big choir, but recording all the voices separately is a bit tedious. So we did an experiment that's kind of a scaled down version of that, where we have a choir of 12 voices, where 8 of the voices are clones and 4 voices are real voices mixed together. And for each of the 8 clones, we use 2 minutes of adaptation data. Okay, thank you.